Let's look at this fish. Look at that, it looks like a torpedo coming at you. It's a fish that likes to eat fish. Does it look like the boat up there? Yeah, it would look weird if my pipe was that big. Has a tongue, but they do have an amazing sense of touch that we don't have. And I'm jealous of it. You've seen schools of fish where they all turn at the same time? Can your mom do it when you're a little kid trying to get in trouble? Yeah. Fish never drinks and pees continuously. It never stops peeing. Pees. All right, so we'll go ahead and actually dissect this guy now.
Yes.
Many different species of fish as fishes. All the fishes in the sea. Agnathia are the ones that don't have jaws. They have a cartilaginous skeleton. They don't have scales. And they have a sucker on the bottom that they grab on with. They're kind of predatory. They have anticoagulating saliva. So they can hook on and just become a parasite on another fish. The chondrichthyes are the cartilaginous fish. That's the sharks, rays, skates, ratfish. They have a cartilaginous skeleton, skin covered with denticles. So they don't have scales, but they have teeth all over their body. The thick skin supports their flimsy skeleton. The skin is elastic and aids in their movement, and it kind of springs their body back when they arch on one side, then the skin helps pull it back. So it's like elastic. It's a rubber band. And the jaws aren't connected to the skull, and they can become unhinged, protruding forward, allowing for a wider gape when feeding. Let's look at this fish. And it has some fins, and there's different types of fins. Some are rays and some are spiny. You didn't even know this one was here. It's so hard to get out, but it's going to pop up. Look at that. Now feel the difference between a ray and a spine. Don't be shy. The rays are soft and the spines are sharp. You don't want to get poked by the spines of one fish out here in particular. Anyone know?
Catfish.
Yeah, the lionfish, the catfish. We don't have those here.
Stonefish.
Scorpionfish. We don't have stonefish here, do we? I think they're scorpionfish.
Rockfish.
The stonefish are down in Australia, South Pacific and all that.
There is rockfish.
So this is the spiny and this is the ray. And they're both dorsal fins. Now we have some fins that stick out the side. And these are the pectoral fins. This fish uses the pectoral fins to steer with. They're not using them for propulsion. Can someone think of a fish that often uses them as propulsion? Parrotfish.
Seals?
I don't know. Probably. Flying grenard?
Yeah.
No, I don't know what they do with those fins. Did anyone see them folded out today? They look like Batman cape or something. They're so cool. The ones that use it for propulsion, they have a big paddle-like thing on it, and they actually have a great big muscle inside that has got a lot of blood going to it, so they can use that as their means of locomotion. This is using it as a means of steering. And what's this fin's name?
Tailfish.
It has a more precise name, though.
Tailfin.
No?
Is it a tailfin?
What?
Anal fin?
No, the anal fin is right here. This is the caudal fin. The caudal fin. And then we have paired ventral fins. And are they spiny or ray? Well, it feels like there's one spine at the first and the rest is rays. We've learned a bit about the different fins, but how does this fish swim? It has a sinusoidal motion as it goes through the water. Whoops. And it increases at the back end. And it uses these other fins just to keep it from rolling over if it needs to, and to steer with. this is a fish. This is a jack. I'm going to call it an amberjack. It's a predatory fish. It swims most of its life chasing after things to eat. So it's eating other fish. This is a piscivorous fish. Likes to eat fish. It's a fish that likes to eat fish. Piscivore. Pisces is fish. If you want to eat another fish and you're swimming around, you're hoping to catch it, what's something that would be good to do?
Speed.
Speed, definitely.
Agility.
What?
Agility.
Agility.
Oh, big eyes.
So you can spot your prey. Very good.
Quick turning.
Excellent.
Streamlined.
Very much a streamlined body. Look at that. It looks like a torpedo coming at you. If you look at it from underneath, does it look like the boat up there? Is it white?
It's a camel.
And now if we look at it here, does it look like the boat? No, it's black. This is a counter shading camouflage system. Dark on top, light on bottom. So if you're underneath it and the light's coming from the surface, now it's blending in with the surface. If you're above it looking down, it's blending in with the bottom. So counter shading camouflage. Let's talk about the different senses this thing has. Come up with all of them that you can think or see of.
Smell, sight.
So it has eyes. Are they big eyes or tiny? They're pretty big for its body. I would look weird if my eye was that big. But yeah, good size eyes. You said smell. Does it have a nose?
I can't see the front. Nope.
In fact, it does. It has two openings, an in-current and an out-current hole. And it has it, and it can sense the smell that way. So, can it like smell another fish to eat or something? Why does it need to smell? Probably. So that's a chemoreception, light. So photoreception. What other senses?
Scales.
Scales are a sense?
Phenomenal.
They taste things.
Maybe. Maybe they have a tongue.
They need taste.
I don't think they choose to not eat things that get in their mouth, but this guy has a tongue.
So taste.
Big mouth.
Taste, sure. So that's another chemoreception, taste.
Give him a kiss.
Has a tongue.
For the monkey.
All right. Any other senses?
Touch.
Yeah, I'd say touch, but they don't really.
But they do have sensation under their skin. They do have the sensation of touch. So he was kind of saying scales, but that's just the skin they have. If you touched it, they would feel that. But they do have an amazing sense of touch that we don't have. They have something that we don't have, and I'm jealous of it. And that is, they have a row of neural mast cells that's like a pit that has a little hair in it that can feel both electricity and it can feel pressure waves.
Electroreception.
Well, it goes along, it's called a lateral line, and you can see it.
Wow.
And that allows the fish to do things like know when a predator is coming at it, or you've seen schools of fish where they all turn at the same time, and you wonder, how did they do that? They can feel it. They all just do it. They can feel everybody turning at the same time, and that's with this lateral line. So that is a vibration type detection. It's like being able to close your eyes and feel what everyone else is doing without your eyes closed. Can you do that?
No.
Can your mom do it when you're a little kid trying to get in trouble? Yeah. Any other senses that we have that maybe they have? Oh, I thought you said something.
Hearing.
What?
Hearing.
Hearing. That's it. they do have ears. They have an ear bone, and it's inside their head, and it's called an otolith. And every year that they live, they get a ring on their otolith, and you can age a fish by counting those rings on its ear bone. Now fish, they swim by having greater thrust than they have drag. And they have a great big body for the locomotion of swimming. All of this is mostly muscle for swimming. And then there's going to be some eye and a tiny brain and some gills to get oxygen and some very simple digestive system, because it's very easy to go from fish to fish. If you eat fish, it's easy to take that stuff that you ate and turn it into what?
Energy.
Fish. The fish eats the fish to make fish. It's very hard to eat things like algae and make fish out of it. You have to eat a lot of algae and process it and get different things to come together, and their digestive system is very long, with a very long intestine and multiple stomachs. But a piscivorous fish, very simple. Alright, as we look at the fish, how does it breathe?
Jules.
It has gills, and they're inside here, and it has a operculum cover on the gills. And you can see that they're bright red inside of there, very red. And this fish will it'll be swimming along, it'll just open its mouth, and that forces water in, and then it opens its operculum and it lets it pass over the gills. So the water current is going this way. And there's this thing called a counter-current exchange system in their gills, where the water's going that way, well, the blood is going to go that way, inside of the gill. So when you look in the gill, and you can imagine it being arranged so that the blood is traveling in this direction in a counter-current system. And that allows the fish to get 100% of the oxygen out of the water that passes over the gill. If they were going in the same direction, because it's traveling with diffusion, higher concentration to lower concentration, they could only make it to 50%. They'd only be able to get half of the oxygen out of the water. But by going in an opposite direction, there's always a downhill gradient. When they've gotten most of the oxygen out of the water and it's only 10% oxygenated, well, that's the very first blood that hasn't got any oxygen in it at all. And so it's a downhill gradient. It can still go and diffuse into the bloodstream. Up at the top, almost all of the blood has oxygenated. Well, that's the freshest water. So it's 100% of the oxygen in the water. And it's still, so you can go from 100% to 90% on a downhill gradient. You can go from 10% to 0% on a downhill gradient. But you can't go from 50% to 50% and have anything happen. So they have to go in different directions. If they were the same direction, they'd meet in the middle, and that'd be that. So they can get twice as much oxygen out of the water than they can if they were going in the same direction. Anyone seen this old movie with Kevin Costner called Waterworld?
Yeah.
And he grew gills behind his ears? Yeah, that's just total fiction. It makes people stupider, because you get enough oxygen out of the water, because the water is only like 0.3% oxygenated. The air that we breathe is 22% oxygenated. So there's a lot less oxygen in the sea. So even if you wanted to have gills, you wouldn't be able to have gills big enough to support our big brains and high metabolism. Your gill would have to be bigger than your body to get all the oxygen that your warm-blooded, hot-brained, big-brained, constant temperature body requires. So these things aren't hot-bodied, and they aren't big-brained, and they don't require near as much oxygen as us. So they can get by with gills. But can anyone think of an example of a big-brained, hot-bodied sea creature?
Dolphins.
And do they have gills? Now they have to come up to the surface and grab that nice 21%.
Whale shark.
Yeah, that's a big fish. It's just a big fish. It's not a
Very big
big brained, it's not a hot-blooded, it's just a fish that looks cool.
Whales.
Fish. Whale shark.
Global.
That's just whales.
Whales are like dolphins, they're mammals. So those things that are constant temperature and big brain, they can't have gills. So Kevin Costner either had a tiny brain or it was fake.
He had a tiny brain.
Now the eyes have a second layer in the back of it that allows it to catch extra photons of light. It's called a tapetum lucidum. Everyone say tapetum lucidum. It's a layer of guanine crystals in the back of the eye that give it a second chance to capture stray photons that go in. Anyone ever seen a cat's eyes glow at night in the headlights? They got it too.
But Jason, I have a question.
Yes.
So you said water has to flow through the mouth, exit the gills, so you can pull out the oxygen. So that means they don't sleep. Do fish sleep? Is my question.
Yeah, fish sleep. They can do that just like you can breathe at night, right?
Mhm.
They just open their mouth and breathe. But can anyone think of an animal that can't fully sleep at night in the sea? Now, sharks are fish.
Oh, dolphins.
Yeah, dolphins can't. They have to keep part of their brain awake to go up to the surface to breathe all the time.
Oh, orcas. Same thing.
Orcas are dolphins. They're big dolphins.
Or turtle.
What?
Turtle. They're
A
always coming
turtle?
to breathe.
Yeah, they have to come up to the top to breathe as well. So some of these fins are for preventing roll. Some are for steering. And it's all yaw, pitch, and roll. That's what these things are doing for us. But this fish has a symmetrical tail. Some fish have a very non-symmetrical tail, like a nurse shark. The top part is way longer than the bottom part. For fish with a symmetrical tail, they're usually cruisers. It's very efficient and they swim continuously. When it's long on one part, not on the other, it's more like a burst swimmer. A burst swimmer usually stays in the same place, but then darts out really fast to eat something. Whereas a cruiser swims continuously and they have very red muscle inside of them. The burst swimmer would have white flesh. So think of a lionfish. Is that a cruiser or a burst swimmer? Nice white flesh, and they just sit and wait. They're kind of a sit and wait predator.
What about barracudas?
Boy, I think they're a sit and wait predator. Now, is there any fish that have warm blood? They're warmer than the surrounding water.
No.
Yes, like the tuna. They're not warm-blooded, but they're warmer than the surrounding water. So if you're conformed to the environment around you, but you're warmer, you're still ploikiothermic. You conform to the environment, but you can just be warmer. And they're ectothermic. They derive their heat from the environment. But some fish, like tuna, are much more hotter inside than other fish, and that allows them to do something to their advantage. Any idea?
They're hotter on the inside.
They're hotter on the inside than other fish.
So I'll go faster.
They can have their muscles work more efficiently and swim faster and catch those fish that don't have that advantage. So yes, that's exactly it. So they're not warm-blooded, they're just warmer. They're warmer than the sea. They still conform, but they're higher. So if the sea's 30 degrees, they might be at 50 degrees. If the sea is 80, they might be all the way up there at 95 or something. But they're not at constant temperature. Whereas a dolphin or a human, we have a constant temperature because our brains demand it. They're like, dude, anyone ever felt really bad when their body isn't conforming to the temperature it's used to?
Yes.
Yeah, like a fever or hypothermia. So that's why a tuna has a warmer body temperature so that its muscles can work better. That's why we have a warmer body temperature so our muscles can work better. They can hold more oxygen, they can just, everything about them functions better at a warmer temperature. Now, how many of you like to drink seawater?
Not really. It's a little salty.
Much flavor.
How many of you like to drink fresh water? Like
Yeah,
a
not much
cool
flavor.
mountain stream fresh water? You don't like it?
It tastes the same as salt water to me.
What do you prefer when you drink?
Uh,
Air. Alright.
Can you
Well,
drink air? It's a gas.
You could, yeah, you could
Technically,
liquefy
yes.
air. It might freeze you as it went down.
Nonsense.
exactly.
Okay, this fish lives in the sea, and it lives in the salt water. Would you believe that it drinks the seawater continuously? It never stops drinking the seawater. It opens its mouth up and swallowing seawater. It's drinking seawater always. It loves the seawater. It drinks it, drinks it, drinks it, drinks it, drinks it. And then let's think about a nice bass up in the mountains or a rainbow trout. Anyone ever caught one of them? All that beautiful fresh water, you know that they never ever take a sip of it. They never drink a single drop of that fresh water. And the sea fish, they drink continuously. But there's something else different. The fish in the sea, they never pee. They are drinking their whole lives and they never
They're
pee.
trying it like on a cellular level to keep the like membrane.
They're having trouble with osmosis. So they're losing through their gills all that water all the time. And on a freshwater fish, because their solutes are higher than the surrounding water, their gills are bringing in solutes all the time into their body, and a freshwater fish never drinks and pees continuously. It never stops peeing. It pees, pees, pees. It's getting way too much fresh water through its gills than it can handle. A saltwater fish is getting not enough water, and it's coming out of their gills all the time. So they're having to drink all the time, and it's going out their gills, and they never pee. A freshwater fish never drinks. It goes in their gills, and they have to pee all the time. Is there any fish that can go from salt to freshwater and back?
Bull shark.
Bull sharks, yeah.
Salmon.
Salmon.
Certain types of catfish.
Yep.
Trout.
So they have to change their physiology in the middle of that.
I was about to ask you, how do you do that?
Practice.
Well, some of them it's a one-way trip, like
You
the
guys have to
salmon.
think
But
about
there's
it.
some salmon that can do it multiple times.
Oh,
All right, so we'll go ahead and actually dissect this guy now.
Yay!
I'm going to go in through the anal region.
Good spot. Are we gonna eat some of it?
Yeah, I'll be nice and careful.
Well, I can live some fish.
I tell him to close his eyes, but
What's
he
your
doesn't have
preference,
eyelids.
Scuba?
Below average.
Do you guys compete
I'm
over
so
who's the
bad.
funniest comedian?
I'm
Yeah.
a master
Yeah.
at chicken. I can go through chicken. That's me tough.
What's your favorite vegetable?
Okay, so we have its internals.
I had to do that with dogs.
But let's look inside this cavity now where his
Nice
internals
one.
were. I wasn't able to get the internals out without popping the air bladder. Okay, here would be a closed air bladder, and it uses that for buoyancy control. It has a VCD. Some fish have a air bladder that is open to the throat, and they can go up to the surface and gulp air down. This one has a one that's closed, and they have to have a special organ to release oxygen into their air bladder, so it kind of does it at a slower speed. So if you pull a deep sea fish up fast, all the air expands and their eyes pop out and they look all horrid by the time you get them to the surface. I cut off its throat. Right here would be his heart, and this is going to be his stomach, his liver, to purify the blood before it goes to your body. So the very first thing that blood does when it leaves this combo of stomach intestine, or it just absorbs it all there in the one spot where it's. Some fish have complex intestines. This one had a stomach that's also its intestine. But once it absorbs those nutrients, it has to go straight to the liver to detoxify it before it goes and poisons the rest of its body. So that was the stomach, and the rest of this is the liver, and the liver is huge. It's way bigger than the stomach. It's got such an important role here to detoxify that blood before it goes to the rest of the body. I don't really know what type of toxins they have in them, but apparently it's important. There it is. So the fish has a 2-chambered heart. How many chambers do we have?
4, I think.
We have a 4-chambered heart. Okay. They have gill rakers to support their gill arches. And this is all for water diffusion to pass over, to have lots of surface area, to get the oxygen out of the water. The gill rakers, though, they also function very well to help steer the food that they catch down their trachea, esophagus. Which one goes to your stomach?
Probably your esophagus.
Your esophagus, all right. Down to the stomach. So it steers it that way. Yes, you can pass those around, touch them. We didn't really look at how nicely articulated this mouth opens. All right, let's take a look at the fish's eye. And excuse me, I'm going to have to make some crunching noises to get in there without hurting the eye.
Yeah.
Smells like
Get it,
doggy.
Jason. I'm good. I've dissected a lot of stuff. So.
Give it a smell.
Wow, it looks so pretty on you. Yeah. It's like a little diamond ring.
Jason's just manhandling that fish. Christ.
Well, I'm trying to do the very complicated thing. And that's to get to the brain.
Oh, it's hard.
That's a very tiny brain.
Yeah, they